Okay, so I had to wander off and do like 2 or 3 other things, but I think the last thing we got through was measuring the power in this beam with the thermal meter, the thermal head for the meter, rather. So the next thing I want to do is to take a look at the wavelength that this thing's emitting. And I'm going to do that with a spectrometer. It's the same as the ones that we've been using for the Planck's constant lab, I think it was. So I have one right here. Little USB spectrometer. These are kind of ubiquitous now in optics labs. They are, I mean, dinky. It's not a scientific instrument. We have an Ariba Giovanni Von spectrometer and camera set up here in this lab for scientific research that has really good characteristics. It's a powerful instrument. But for diagnostic stuff, kind of figuring out what you're doing, these little USB spectrometers are extremely useful. It has a dispersive component in it that will take a beam of light coming in with whatever colors are propagating in that beam. The beam comes in, hits the dispersive element, probably a grating, and that separates it out so that the colors spread out based on their wavelength, right? So red comes in and goes one way, blue comes in and goes the other way after they strike the dispersive element. This is a grating. It's an old one. I've had it since I found it, I think, at a surplus sale in San Antonio. There's a ton of Air Force bases in San Antonio. And so it used to be one of these places where you could just find really great scientific equipment kind of just sitting on someone's shelf, because historically you could kind of go into their surplus warehouses and just say like, all right, well, the U.S. Air Force had to surplus out these RF function generators for various reasons. Maybe one of the buttons was broken. Maybe they work perfectly, and the Air Force has to constantly keep a certain amount of turnover with their equipment so that they actually have stuff that has only been used for 2,000 hours to make sure that it doesn't break down when it's absolutely needed. So there was tons and tons of surplus high-tech stuff floating around San Antonio. And that's changed now, unfortunately. It was great for the universities in Texas. You could go down there with a couple other grad students and pick up stuff for your lab. But even putting that aside, the surplus market for old, a few years old, 10 years old, 20 years old sometimes, just depends on the stuff. The surplus market for old electronic stuff like that was amazing. Anyway, I've got a grating here. It has maybe 600 grooves per millimeter, maybe 12. No, I think this is, if I'm looking at it right, it's 1,200 grooves per millimeter, which is a very high density of grating grooves. Let's see what it looks like. Rainbowy, right? That's because the white light from those fluorescents, after they goes to the phosphor that whitens it up, the white light is getting separated out based on its wavelength. These are cool gizmos, but they're super delicate because they have all these tiny grooves scratched in a periodic fashion on the surface. So if you get this thing dirty, you're in trouble. You can't clean it the way you can clean a mirror. Some mirrors are just a very thin layer of aluminum deposited on the surface of glass. Those are the ones we use for ultra-fast experiments. You can't clean those either. So they're fragile. But you can see how it works. It's essentially like a prism, but it works in reflection instead of transmission. Okay, and incidentally, the math for how that all works is well described by Bragg scattering, Bragg diffraction, right? So that's another thing we should revisit. We talked about it, and I said, go write something about that. Go read something about it. Well, you should, because it shows up everywhere. Like if you want to work in material science, you'll use X-ray diffraction to study the crystal structure of materials. If you want to work in biophysics, maybe you'll study proteins, and you'll do the same kind of thing with X-ray crystallography. If you want to work in light, you use Bragg diffraction for tons of stuff. We have on the other side of the table here we have a couple little gizmos over there that are acousto-optic modulators. So an AOM, acousto-optic modulator, is just a chunk of glass or a crystal, in this case tellurium dioxide, that you send the sound wave through. Well, it's sound, it's pressure. So the pressure inside the crystal changes its local index of refraction. But a sound wave is a periodic wave. So the pressure wave is a periodic wave. So the changes in the local index of refraction are also periodic. And what that means is you've created a periodic grating inside this crystal, and light will scatter off of it. So we can use sound waves to diffract light, and we can control how those sound waves behave by changing the frequency, amplitude, or phase of the sound wave we send into that crystal. Bragg scattering, it shows up everywhere. You should absolutely really get how this thing works by the time you graduate college. Okay, that's my sermon. So we have a spectrometer, and I'm just going to plug this thing into the USB port on my computer and run it with Logger Pro. So let me switch over to Logger Pro. Now that I'm off the main screen, I can wear my glasses so I don't get the glare coming off and then I find it really distracting. All right, so Logger Pro doesn't have any kind of sensor connected to it. I'm just going to plug the USB spectrometer into the USB dongle that hangs off my MacBook. Let's see if it automatically detects it. Maybe. There we go. So you can see up here in the upper left, there's a little spectrum indicated. All right, so if I click this thing, it brings up some options, and I would have thought that it would let me change them. But yesterday when I tried, it wasn't allowing me. Oh, it'll do it. Hooray. So let's reduce the integration time. Nope, not that far apparently. Looks like 15 milliseconds is the minimum. Okay, sample time. This should be called integration time. What it means is I'm going to put a sensor into my experiment. I'm going to let it collect data. If I just stick it into the experiment for a split second and remove it, it will have created a split second's worth of data. If I can put it in there for a while and let it accumulate data, instead of trying to measure something with 1 or 2 clicks of the instrument, you know, it'll have instead 1,000 clicks. In this case, a click means a photon count, but I'm using it so you think about a Geiger counter. All right, so if we let this thing integrate for a longer period of time, we'll record the effect that more light has on the CCD. There's a CCD in the spectrometer. Light comes into the spectrometer, hits the grating, is dispersed, hits the CCD. The CCD records how much light each pixel gets. From that, it can determine how much light you had at each individual wavelength, right? So integration time lets us say record data for a longer period of time, but 15 milliseconds is the minimum that this spectrometer can do. All right, wavelength smoothing. This means whatever the output is, I'm then going to run an algorithm that will just sort of average it locally. So like this point will be averaged with the 2 adjacent points in order to get rid of the spikiness in the function. That spikiness is partially real and partially an artifact of the way we're going to do a janky, really, really messy job of aligning the beam into the spectrometer. If we did a good job, we get a real measurement of the spectrum of the laser. If we do a bad job, we'll get a result in 20 seconds. So we're going to do a bad job, but I'm not going to change the wavelength smoothing because I want my real information. I don't want an algorithm to tinker with it. Samples to average. Okay. The way to think about this is I have my 15 millisecond shot, and then I portray that data. Take another 15 millisecond shot, portray that data, and so on. What I could do instead is say, take 10, 15 millisecond shots and average them. That will help to reduce the noise in the measurement, because if it's just a random fluctuation that appears in one spectrum, then the fluctuation should not look the same in the next subsequent spectra. So averaging it should diminish that effect. I'm not going to bother with it for now. Wavelength range. The camera. The spectrometer is sensitive from 350 to 900 nanometers. So if my light is shorter in wavelength, bluer than 350 nanometers, which means it's heading into the UV, I won't be able to observe it with this instrument. I don't think there's UV in here for the reasons we've already talked about. If it's longer wavelength than 900 nanometers, we won't be able to detect it. 900 nanometers is in the near infrared. People say, oh, human visibility runs from 400 nanometers to 700 nanometers. That's made up. That's pretend, because your eye doesn't just turn on at some wavelength and turn off at another. It has some kind of function where it responds at different intensities to different wavelengths. So if I have an 800 nanometer or 900 nanometer laser beam, if there's enough power in that laser, I'll see it, because the laser is an intense form of light. It's coherent light. If I just had regular incoherent diffuse light at 800 nanometers, yeah, my eye wouldn't respond to it. But if it's a laser, my eye can see the 800 nanometer light and just says, oh, it's deep red. Same thing will happen at the other end with UV, although eventually if you go deeper and deeper into the UV will just damage the front side of your eye and you won't see anything ever again. Anyway, this is the total wavelength range that this instrument can span. Let's just start with that. Intensity correction. I assume that this is dealing with the fact that the sensor inside of the spectrometer is probably a silicon CCD, which means that, like those silicon photodiodes, like this guy, its behavior is actually determined in part by the wavelength of the light that hits it. All right, so we can figure out what that behavior is and then correct for it. I'm not going to bother with that at the moment. I mean, it would give me perhaps a more accurate result, but I just want to find out what the wavelength of my light is. So I want to be doing the least amount of stuff to the phenomenon that I'm trying to measure. All right, so let's just stick with these default settings. And we're going to start collecting spectra. All right, so let me wave this thing around a little bit. My spectrometer has a fiber that I've run into it. That fiber goes into this part of the spectrometer. So light that is aligned into the front end of the fiber will be transmitted through the fiber and into the spectrometer. It'll be dispersed. It'll be recorded on the CCD, and the instrument will tell us how much light we have at each wavelength. What does align mean? Well, it means that a fiber optic has a core that is, I'll tell you exactly, in this case, the fiber core diameter is 400 microns across. So I have to have a pencil of rays of light. A pencil is just a way to describe like a bundle of rays going together that is aligned into that 400 micron core. For a fiber optic, that's actually a really wide core. You might have expected something more like 40 microns if it were a fiber to be used in a laser application. This is wide because we want to make it easy to get light in there. It's just like a funnel for light. Okay, I removed the protective cap. I could wave this up at the fluorescence, see if I can get any light in there that way. Let me get a little tiny bit. I got it a second ago to jump. There we go. Those emission lines are probably the lines from the mercury vapor in the fluorescent light. We could actually even use those to calibrate this thing because everybody knows the wavelengths for mercury. They're very well tabulated. But I'm not interested in that at the moment. All right, so let's wave this thing in the vicinity of our laser beam. Again, shiny surface, shouldn't stick it in the laser beam because the laser is going to hit the surface and reflect, and then maybe it hurts somebody's eye. I already know that this is an eye-safe laser, but that required some exterior knowledge on my part. All right, so I'm going to align this thing into the laser, and I can see there's a couple features, right? But one of them is much more prominent than the others. All right, so what's my guess? My guess is that the gas that's lasing in this thing can support emission at a range of wavelengths if the cavity permits it. Now, even if it only had that one feature that's more prominent than the others, let me see if I can get it back. I actually don't want to blow it out again because then I'm getting blooming just like with the other CCD stuff. All right, so there's that one wavelength that's enormous compared to the others. But even if those other ones were there, Actually, hang on a second. Let me talk about this another way. Even if we forgot about those other ones that are pretty far away from it, that one big peak is actually made up of several peaks. They're just closely enough spaced that the spectrometer can't resolve them. All right, but we've got this wavelength. If I get too much light in there, the CCD blooms and adjacent pixels start to detect light. Well, they don't detect light. They detect the electrons that were generated in the pixel that is supposed to be getting hit by the light. So that's blooming again. A word of caution is that it's possible to send enough laser light into a spectrometer that you burn a component in there, probably the CCD. Again, I know how much power is in this beam, so I know we're not going to do that. But when we get that light in there, where are you? It looks to me that that's something like, I don't know, between 520 and 560 nanometers. So let's change our wavelength range to just look at those wavelengths. You can see it's really easy to overwhelm the sensor again. So let me go grab some more neutral density filter stuff, and we'll stick that in the beam path. It looks like sunglasses material. I mean, it essentially is, except somebody's taken the effort to make sure that it actually diminishes light intensity at all wavelengths in its range equally. It's got an optical density of 0.80. This was made by the Newport Corporation about 1 trillion years ago. Oh, and unlike sunglasses, this stuff is super expensive just because of that careful analysis, making sure it does exactly what you think it does. There are two different kinds of neutral density filters. Some have metallic nanoparticles in the material that just scatter light, so they knock down the intensity of the beam really effectively, but they also trash the mode quality. So instead of having a nice smooth Gaussian, you have a Gaussian. You know what I mean? Like, it gets a lot of spatial noise in it. The good kind has, I think, carbon film in it, if I remember correctly. They're more prone to being damaged by heat, because if I put one of these things in a laser beam and the laser has a lot of light and it has to absorb a lot of that light intensity and then re-radiate it as heat, maybe it absorbs it too much too fast and heats up and cracks. But again, we're working with a laser with minuscule amounts of power in it. Minuscule, but still enough to blow out that sensor, huh? OD of 2.0 plus OD of 0.8, so OD of 2.8. Dark. With that much OD in there, I can actually still see the laser, but I'm having a hard time getting the beam right into the tip of the fiber, in part because I didn't grab a proper holder for these things. I'm just trying to do 3 things with 2 hands. So I'm going to remove a little bit of the OD. Okay, optical density of 2. OD of 3. Okay, with an optical density of 3, we can see that this beam is pretty definitely giving us light between 540 and 550 nanometers, and it looks to me like it's roughly centered at 545 nanometers. Again, I could do this a little bit better. I could actually make sure that I lined up the beam into the fiber just exactly, and I could get just the right amount of optical density in there so that I could see the shape of the beam pretty clearly. It's the shape of its spectrum, but it's just more fuss than I need to do for what I'm actually trying to do at the moment. All right, so let's take that data and use it to do something useful. So we know that this light is about 545 nanometers. All right, so what I'm going to do now is say I have this information. I want to turn that into something I know. I know the wavelength of a Heaney laser that I'm used to looking at, 632.8 nanometers. You know, quantum mechanics determines that. And that's the red Heaney laser spectrum, as long as I don't come in and perturb the atoms with an intense magnetic field or electric field or something like that. So what emits at 545 nanometers, give or take? Well, I know this is a gas laser. I am, from previous experience, pretty well convinced that it's a CW laser, although that doesn't tell me much because I could actually build a pulsed Heaney laser, for instance. Those exist. I have an ancient Q-switched pulsed Heaney laser floating around in my lab, but I hate running it because some piece of it is getting hot and outgassing something really vile smelling. So I don't know what that is. I don't think it's good that a laser smells bad. But I have this laser. It's producing green light, and I know the wavelength. So I'm just going to look that up. So I went to Wikipedia and searched gas lasers, and it provided me a tabulated list. I think that's what I looked up. I can't remember 100%. And it turns out that 545 nanometers is the characteristic emission wavelength of a Heaney laser, because neon can actually emit multiple different wavelengths of light. So when we see that red laser light from a Heaney laser, that's 632.8 nanometers. But the Heaney laser can emit at different colors. We then typically do something with the laser design to cause it to emit just at one, or maybe if we want it, 2 wavelengths, and to knock down the other wavelength emissions. So this laser that's hitting my hand is actually also a Heaney, and I know its wavelength, 545 nanometers. That means I can go back and actually measure the power it's emitting. Photodiode sensor. The meter. And I set the meter to actually detect light at 545 nanometers. All right, that's all set. I was actually trying to do something else, but I need to not try to kill two birds with one stone. So I've got my photo sensor. I'm going to look at this. It says, oh, when it's not being hit by the laser, there's 19 microwatts of light on it. If I cover that with my hand, it drops to minus 1.7 microwatts of light. There's some error in this. I need to re-zero the sensor, and I can do that just in the software that runs on the meter. I'm not going to bother. 19 microwatts of visible light's not much, so I'm going to say that's just my noise and my measurement. I'm not going to worry about it. I could get this done better, but for the moment, we're fine. And then with the beam actually hitting the sensor, it's recording 0.263 milliwatts, 0.264, 0.265, 0.266 milliwatts, 0.267. Is that drift due to the sensor? I don't think so, actually. I would expect it to have random noise on the sensor. There's not enough thermal stuff going on here to change the way that the PN junction is working. So I think that I expect noise on the sensor to be random. It should go from 0.263 to 0.264 to 0.260 to 0.265. It should be jumping around. The laser is probably still undergoing thermal effects. As it heats up, as the tube heats up, it changes its length a little tiny bit. And that is a very definitely observable effect with this kind of laser. There are two mirrors at either end of the gas cylinder that actually form the so-called laser cavity that the light bounces back and forth in and builds up in. That's how we get the intense light for a laser. The issue with this is that as that length changes, the characteristic operation of the laser also changes, and that might cause it to not reach a steady state temperature at some asymptote, but instead to do this. So stabilizing Heaney laser is actually an important part of making it into a really useful scientific tool. The ones you buy, you know, the surplus things pulled out of people's x-ray machines, they're not usually stabilized. We can do it, and I actually want somebody to take one of those old Heaney laser tubes and stabilize it. All right, so I have like one other thing I want to mention. If we were crafty, maybe when we turned on this laser, we would have said, hey, hang on, just wait a second. With actually getting my without actually getting my eye down there at the level, you know, maybe in the eye. Sorry, Zoom is doing some weird stuff. I can still kind of see that. Let me try moving the camera. All right, so I hope you could see that reddish glow in there. That reddish glow is the same as the reddish glow that was inside the Heaney laser tube we looked at earlier, the one where we had the cover cracked off of it. So we might see that characteristic fluorescence and say, hey, wait a minute, that looks like the fluorescent emission from neon. So I think that this tube has neon in it. And then we would probably say, well, you know what, it's not a helium cadmium laser, which is a kind of laser. And if I remember right, that's also a green one, although I could be wrong. It's been a minute. I bet this is some kind of Heaney laser. The very first Heaney laser that was built was at Bell Labs in 61, I want to say 1961. And it emitted at something like 1.3 microns, 1.1 micron, if I remember correctly. So a longer wavelength than the stuff we're looking at and into the near infrared. Okay, this was 3 minutes worth of fiddling around with instruments spaced out over an hour. So hopefully it was scientifically interesting and engaging. But at this point, I have to wrap it up and turn our attention to other stuff. Thanks for listening and paying attention. I hope you did. I hope this was interesting.